Good morning, everyone. It's a great pleasure and honor to give a talk at Stephen's birthday conference. And I'm also going to thank Eiichiro for giving such a nice introduction to the physics of the cosmic microwave background. And what I want to get into in this talk is the level of complexity that we come to when we try to probe fundamental physics with cosmological data, and particularly the cosmic microwave background. We've established the cosmological model as we know today using data from the cosmic microwave background, and in particular the temperature fluctuations. So all of this evidence for inflation that has been established comes essentially from the scale of fluctuations. Where we need to go next in order to probe the nature of this phenomenological cosmological model we've established is much more difficult, and it involves trying to do not just cosmology, not just fundamental physics, but what I call mud wrestling. I'm going to show you some of that mud wrestling and show you how the sausage is made, essentially. So let me start by saying that some of the work I'm going to present at the start of my talk come from the hard work of a lot of people. Is the Planck collaboration. Here is some of the Planck collaboration. So it's the work of a lot of people, and especially the students and postdocs that work on this data. So to start with, let's pause again and look at the history of the universe. And so most of what we've learned from the cosmic microwave background has come from this time, 380,000 years after the initial time. And if we were to detect gravitational waves, so as Eiichiro showed, inflation generates at least two types of waves, density modes and tensor modes. So if we could detect these tensor modes, we could rewind all the way back to the very, very early times, the era of inflation and the end of inflation. So I want to show you, first of all, what we have learned from studying the light from here, and what we could learn if we could actually disentangle all of these foregrounds and lensing and all these effects that we just talked about, rewinding to the very early time. So I'm going to skip through most of the detailed history of the cosmic microwave background and just show you how the data have improved. This is essentially jumps in decade, just showing data from space. It's an incredible set of measurements that's enabled by the technological improvements in detectors and the systematics and instrumental control of the ability with which we can measure these fluctuations in a sensitive way. And as Eiichiro showed, if you have velocity gradients at the last scattering surface, you're going to generate a temperature quadrupole, and that generates an E-mode polarization pattern. So if you then look at how this pattern is correlated with the hot and cold spots of the cosmic microwave background, you can see that here's the intensity, and here is the polarization, the two Stokes parameters. So here we're just showing Q, I think. So if you have a cold spot, you are going to see a tangential pattern in polarization around it. And if you have a hot spot, you're going to see a radial pattern around it. So this is stacking the Planck data. This is a theory prediction, and that's the measurement. So it shows you this consistency between temperature and polarization in measuring the cross-correlation between these two modes. And in this kind of really impressionistic Van Gogh-like color scheme, what you see is the hot and cold temperature fluctuations. This map, I believe, has been filtered at quite a large scale, 5 degrees. And you might not see this from the back, but there's a texture on top of that map. And that shows the preferential direction of vibration. That's basically showing E-mode only there. And if you filter the map at different scales, you're going to see that these fluctuations and these preferential directions of vibration are actually present at all of these scales. So this is at 20 arc minutes now. And as, again, Eiichiro showed, there's a way to compress these maps, these 50 million pixels really in the Planck data, exactly into the angular power spectrum. This is assuming that the initial random field is actually a Gaussian random field, but as Eiichiro showed, we know that that is true to a very, very high degree of confidence. So once you do that, you can compress the data into a sufficient statistic and produce an angular power spectrum of the cosmic microwave background. This is an interesting plot. I looked through my notes when I was a PhD student working on WMAP, and this is the first plot of the power spectrum that I could find. And so I call it the first light spectrum. It's the first time we started to fit cosmological models to the data. You can see this interesting discrepancy between the theoretical model and the data. That's because we still had fine-tuning to do in our likelihood. So this is a historical example of what the CMB data looked like at the start of the 2000s. This is what it looks like now. This is the Planck 2015 temperature power spectrum. And so the error bars actually contain both noise and cosmic variance. At large scales, you're dominated by cosmic variance. At small scales, you're dominated by noise. What you're seeing there is the fit to the standard lambda CDM model. And here is the temperature polarization cross correlation. And the red line is still the fit only to the temperature. It predicts this cross correlation extremely well. And this is the polarization E mode autocorrelation. And again, this is just a fit to the temperature. So there's a lot of consistency in the data, and it allows you to constrain cosmological models. What we're doing here is actually a radical data compression. There are quadrillions of measurements of the time stream which gets put into the form of maps. That's 50 million pixels. You compress that down to 2,500 multipoles, and all of that data is fitted by a cosmological model that just has 6 parameters. That's an amazing degree of simplicity to fit all of this data. But before we pat ourselves on our backs, I want to remind you that the cosmological model that we have has what I call 3 tooth fairies. Okay? So first of all, the standard model of particle physics, which we have tested extremely well in the laboratory, does not explain all of this data. We need dark matter, we need dark energy, and we need the initial conditions. And all of these things are phenomenological, and the initial conditions, we have a leading theory that we have tested to a great level of precision. But this is all new physics. And to measure the parameters of this phenomenological model, we do what's called the Bayesian data analysis. So this is not that we can actually directly extract these parts of the cosmological model from the data. We assume a model, and that assumption then falls through to the entire data analysis. And the details depend on the models that you assume, and therefore the priors that you put on the parameters of that model. So we can measure something about the constituents of the universe, the initial conditions of the universe, when the first stars formed, the amplitude of the initial fluctuations, and whether or not the universe has a spatially flat geometry. And when you do that, you get basically contours like this. And something that's really interesting here, I don't want to go into the details of what's on the axis, they don't really matter. The blue and red ellipses come from various combinations of the Planck data in combination with just temperature or also polarization. I want to draw your attention to the green ellipses. So that's just the Planck E-mode autocorrelation data. And that's as good as WMAP. When I first saw that, I was just amazed. But then I thought, that is a demonstration of how far we have come. So the data is now so good that we can start to do both cosmology and astrophysics with the other effects on the cosmic microwave background that's caused by the fact that CMB photons actually go through the large-scale structure of the universe. And in particular, they're slightly deflected by the effect of weak gravitational lensing. This is a very small effect. The deflections are about 2 arc minutes. But because we know exactly how the gravitational lensing effect affects the CMB, it changes its statistics in a specific way. You can extract that effect and invert it and make maps of the lensing potential integrated along each line of sight. In other words, you can get maps of the mass in the universe along every pixel on the sky. And when you do that, you can make a map like this. So this should be thought of essentially like the Kobe map of the first temperature fluctuation map of the cosmic microwave background. This is the start of a new field, really. So what you're seeing by eye here isn't necessarily that there's huge amounts of dark matter over here compared to here. What you're seeing by eye is noise. However, there's a strong signal in here, and the power spectrum of this lensing potential map essentially is detected now at 40 sigma. And just by using this new piece of information, which also comes from the cosmic microwave background, you can replace some of the other data that are more uncertain. For example, the estimate of when the first stars formed and how they reionize the universe. And you can use that to break parameter degeneracies that exist in both the standard model and extended cosmological models. Here is a very recent version of this map. So this is now showing 2,500 square degrees of this lensing potential reconstruction. And this comes from the South Pole Telescope, which is a ground-based telescope in the Antarctic, and also using the Planck 143 gigahertz map. So this footprint exactly overlaps a big galaxy survey called the Dark Energy Survey. So what you can do here is that you're probing the growth of structure through its impact on the cosmic microwave background, but you have also direct measurements of structure in the universe in this galaxy survey. By cross-correlating these two things, you can actually get at the growth of structure and see whether these two data sets are consistent with what we understand about cosmology. And this brings me to a kind of growth area that's happening. And this is actually at the intersection of CMB and also large-scale structure surveys. And this is essentially probing the secondary CMB contributions, the integrated Sachs-Wolf effect, which is essentially the fact that, I think Eiichiro mentions this, CMB photons fall into potential wells and they climb out. And if the potential well changes its shape as that process is happening, the blue shift is not cancelled by the red shift, and you get the integrated Sachs-Wolf effect. You also get the thermal and kinetic Sanya-Seldovich effect, for example, when you have really, really hot gas and electrons in clusters. And as CMB photons pass through this gas, they acquire extra energy, and that distorts the shape of the power spectrum, and as a function of frequency. And also you can get the cosmic infrared background, which is essentially the fact that stars form, lots of stars form, they emit a lot of UV light, it gets absorbed by dust in galaxies, it gets re-emitted, and that also has an impact on the cosmic microwave background. So by measuring the frequency dependence of the microwave sky, you can extract all of these effects. And then you can cross-correlate them with late-time traces of the origin of structure. For example, galaxy surveys or cluster surveys, weak lensing mass maps, and velocity reconstructions. And when you do that, you can try to reveal the interplay of dark and light matter and their evolution and co-evolution with time. So you can try to look for intracluster gas, missing baryons, and you can look at the star formation history of the universe. You can probe halo masses. So at the moment, this field is at the point of making detections of all of these cross-correlations. You can see all of these papers basically in the last 2 to 3 years This is the original detection of the kinetic Sunyaev-Seldovich effect from the Atacama Cosmology Telescope combined with BOSS cluster positions. So that's spectroscopic data identifying where clusters are, cross-correlated with the ACT. This is a version of that same detection, actually done by a PhD student here in Cambridge. This is from the Dark Energy Survey, the survey I'm involved in. And this is from the first year of that survey with 5,000 clusters. And here, purely identified by photometry, not spectroscopy. So that's also possible now. And here is a weak lensing map cross-correlated with a CMB lensing map. So at the moment, we are detecting these effects as predicted by the standard cosmological model at the level of 4 to 5 sigma. In the future, we will be able to use this for both physics and astrophysics as the significance of these effects improve. I want to also emphasize the fact that, yeah, we can make assumptions about the cosmological model, and we can go and measure the effects that are actually predicted by those cosmological models. And it's really important also to probe those assumptions themselves. And in particular, Einstein's theory of relativity explains the local curvature of space-time, but it doesn't tell you the global topology or geometry of space-time. So as we know, when you have statistical isotropy and homogeneity, and you break time translation invariance, you get the standard FRW models. If you actually break isotropy, for example, while keeping homogeneity, you get an extended set of cosmological models, the Bianchi models. And they imprint different structures onto the CMB sky. And you can go and look for these effects in the data. And this is something that we recently carried out with Daniela Sade, who's an excellent PhD student, just graduated from UCL. We tested how isotropic the universe is. So this is the first analysis to actually test the full set of 5 degrees of non-interacting modes, the scalar, vector, and tensor modes from these Bianchi models. And it was the first to use the polarization data for the first time. So basically, the idea is that you've got these scalar, vector, and tensor modes. They predict different patterns on the sky for the temperature, E-mode polarization, and B-mode polarization. And you put that on top of the stochastic fluctuations coming from the inflationary models in the early universe, and then you predict what you would see on the total CMB sky. And then you go ahead and you compare that with the data. And when you do that, you can put constraints on the anisotropic expansion of the universe. And this is the first time these scalar and vector, vector and tensor modes were constrained. And Stephen has a lot of fingerprints on all aspects of cosmology. It's interesting that he was the first to identify that there's a growing tensor mode, which is compatible with very, very small anisotropy in the early universe and large anisotropy in the late time universe. So we constrain that mode. And because this is a Bayesian analysis, we can actually do model comparison as well. We can say, here's the isotropic cosmological model, and here's the fully anisotropic set of degrees of freedom. And you can compare those two models. And the anisotropic expansion of the universe is disfavored by 120,000 to 1. So we put that one to bed. OK. I want to very briefly touch on the fact that there is a dawn of numerical relativity in cosmology as well, especially given that there is a gravitational wave community here. And this is a very different context of using numerical relativity from what you need to do gravitational wave analyses with LIGO, for example. And 2 very quick examples are the ability to possibly constrain physics of eternal inflation by studying the imprint of cosmic bubble collisions on the CMB, and also putting limits on the very, very large scale, ultra large scale structure fluctuations that may actually exist before the start of inflation by looking at the imprint on the quadrupole of the CMB. This is all very nice, everything perhaps holding together, or is it? So recently there has been a demonstration that there is a set of cosmological measurements from the CMB and also from baryon acoustic oscillations that's telling us that the Hubble parameter is slightly lower than what's actually measured from distance ladder measurements based on Cepheid data. So here we basically see that publication year versus H0 measurements. And here is WMAP1. This is the Hubble Key project. Beautiful agreement. Starts to diverge. Okay? And the most recent analysis of either side, quoting their own error bars, including statistics and systematics, start to differ by about 3 sigma. So is this a real inconsistency, or in the memorable words of Wendy Friedman, is it a tension in a teapot? So this is, you know, I'm a data analyst. I'm going to say possibly systematics in one or more of the data sets. Could be astrophysics that are not modeled correctly, or it could be old physics that we have not made predictions from correctly, or else new physics, which is the most exciting option. So given all of those things, I want to go to this part of my talk where I show you how the sausage is made. Let me start with a quote. No one trusts a model except for the person who wrote it. Everyone trusts an observation except for the person who made it. Okay, we do not measure a beautiful map of the cosmic microwave background with only cosmic microwave background in it. We see stuff like this. There's quadrillion samples over 29 months from HFI, 50 months from LFI. We make maps over 9 frequencies. This is from 30 gigahertz to 857 gigahertz. Along here is the galaxy. And you can see that the contribution, mostly from the galaxy, actually changes as a function of frequency. And this is why you measure stuff at a bunch of frequencies. So you can use the fact that the CMB has a known frequency dependence, which is a black body, and take these contributions out. So when you do this, basically the emission at frequency is basically the CMB plus the astrophysical sources along the line of sight. So you can have individual sources. You can have radio emission from the Milky Way. You can have dust emission from the Milky Way. And finally, when you peel everything back, you get back to this pristine, beautiful picture of the cosmic microwave background. And this is the temperature fluctuations. Compared to what we have to do next, this is a booming signal, okay? So we are just beginning to characterize polarized foregrounds. This is polarized synchrotron. This is polarized dust. These are maps that you can make from Planck at the moment. This is not the final story, because there are lots of improvements in resolution and frequency coverage that you have to make before you start to characterize these foregrounds at the small angular scales in particular. The polarized foregrounds are complex and filamentary. They tell you that there's a lot of matter moving in the galactic magnetic field. You can see these big loops. You know, these are structures that are actually quite local to us, and they're projected onto the largest angular scales. And there's also structure that changes along the line of sight, because magnetic fields can be tangled up, and they can depolarize emission from dust. So if you look at the frequency dependence of the galactic foregrounds, here's temperature. This is the RMS brightness fluctuations. These are different components of the foreground emission. And the CMB, if you can see that from back there, is going across it like that. And there's this window in frequency where the CMB pokes above these foregrounds. This is the case of polarization. And so this is orders of magnitude different here. Now the CMB is actually below the foregrounds, average over the sky, at all frequencies. There are fewer foregrounds, at least as we know now, but you have to do a big job to subtract them out. Of course, there are individual patches on the sky that are cleaner than average. So why do we care? Why do we want to do all this mud wrestling? Well, as Eiichiro said, we want to know about cosmic initial conditions. So the fact that the universe is spatially flat has been now tested at the less than 1% level. We know there are scalar fluctuations in the CMB temperature, that they are nearly but not exactly scale invariant. That's greater than 5 sigma, approximately Gaussian. That's at the 10 to the minus 4 level. That's the best and most accurate measurement we have in cosmology. There's adiabatic fluctuations, and we know there's superhorizon perturbations. Inflation predicts one more thing, primordial tensor modes. It doesn't necessarily tell you its amplitude, that's model dependent. But we want to go and measure that. So, but I also say that gravitational waves create polarization, but lensing also creates B-mode polarization. It takes the E-mode polarization and translates it into B-mode polarization, even if there were no tensor modes. But fortunately, this effect varies based on scale. So remember, as Eiichiro showed, these are small scales. These are large scales. Okay. This is the status of the CMB polarization measurements. For many years, we had these upper limits marching down the plot. And this is, again, a logarithmic axis, many orders of magnitude. And then, boom, this happened a couple of years ago. Suddenly, all of these experiments reach a sensitivity that they start to measure something. They can measure foregrounds, and they can measure this lensing signature. This is the lensing signature produced by the standard cosmological model. And all of these experiments are now starting to characterize it. If there were primordial tensor modes from inflation, this is the tensor to scale ratio of 0.09, they would live over here. So if you could measure this signal very accurately, even if there were no primordial tensor modes, you can do fundamental physics with it. You can measure, for example, the neutrino mass. If you then want to measure this at the same time as well, you've got to remove that signal, which we know exists and which we have measured. On top of that, we get the polarized dust and synchrotron foregrounds. Okay? So this is at 100 gigahertz. If you look at the cleanest 90% of the sky, you're up here. And if you look at the cleanest 1% of the sky, you're down there. But there's a huge uncertainty in this. And on top of that, you've got these lensing B modes. So this is the current state of the art of this plot, where you show the B mode polarization versus multipole. And you can see a large number of experiments making nice detections, showing consistency with the cosmological model. The challenge in going from what you measure to the noise you want to reach is immense. Before you even get to measuring anything from the early universe, you start with 300 Kelvin up here from your instrument, and then your atmosphere, and then the galaxy, and then you want to get down to less than 10 nanokelvin in order to make these measurements. And this is not going to be easy, because what we've measured so far from the CMB is up here, and what we want to reach is down here. And as I said, the lensing is an additional foreground for the tensors. So I want to show you some ideas about, if you take into account this foreground uncertainty and the ability to subtract the lensing signal to see if there's anything left over that's primordial, if we actually take into account all of these things, how well you could do with fundamental physics. So in this sense, you want to subtract the foregrounds, and you want to then de-lens. Okay? And subtracting the foregrounds themselves is not very easy either. So this is a plot that shows you that. here is contaminants divided by primordial B modes with R equals 1. Remember, in Eichira's plots, that's long since ruled out. And that ratio is 1 over here. This is showing multipole versus frequency. So there's a minimum over here, but that minimum is not really a minimum. It's already a problem. On top of that, we have experimental design considerations. And given what you can actually achieve in terms of sky coverage versus detector sensitivity versus frequency coverage, experiments try to sit at that minimum. And these experiments, especially after 2020, the proposals that we have on hand actually look quite different from current CMB experiments. They try to do quite a lot of frequency coverage. They almost start to look like radio experiments. When you take into account the experimental characteristics and what we know currently about foregrounds and delensing, here are some kind of takeaway messages you can take from this. So before 2020, basically, you've got your density scalar ratio, the R of 0.001, which Lightbird wants to reach. And here is the lensing signal. This is your noise of your experiment, and this is what it gets boosted to after you subtract the foregrounds. But you can subtract the foregrounds from here down to here. Okay, so you're noise dominated in the foreground subtraction. So after 2020, your noise levels are down here. Foreground subtraction just boosted up to here. So then you're lensing dominated. And your residuals are important because they become roughly the same order of magnitude as your noise. And then you have to subtract the lensing. So this lensing subtraction, the effectiveness of that requires you either to do it internally within your own experiment using CMB data alone, or to use as a proxy a map of the structure formation in the universe. So if you are a noisy experiment, like what we can build now, basically you're better off using the probe or the proxy of large-scale structure, for example, cosmic infrared background map. But if you got low noise, as opposed to 2020's experiments would, then you can delens much better internally, just using your own data. Okay, so that's shown also in this plot that before 2020, you can delens down to here, and after 2020, you can delens down to there. So this is a current demonstration of how well you can do that, and actually showing that you can do it. This is a B-mode delensing demonstration from SPT Pol, and using the Herschel 500 micron CIB map. And they achieved a 28% reduction in the lensing. It's actually dominated by noise in the lensing potential map. In the last couple of minutes, I'm going to show you something that I think is really cool. And I should say this is actually quite speculative at the moment. But can we actually do CMD at commercial aircraft altitudes? Why do you want to do that? So from the ground, you cannot see some of the high frequencies that are dominated by dust, which you need to actually subtract in order to make good CMB measurements. You can fly high in a balloon, and you can use the wind patterns of the Earth in cold places like Antarctica in order to make measurements of these high frequencies and be able to subtract your foregrounds better. But after it does its flight, it crashes to the ground in an inhospitable place, and then you got to wait some time and actually rebuild your experiment, and so your downtime is very long. Satellite is great. It's out there in space, very stable, amazing, very expensive, and you cannot fly the latest detectors because it has to be decided well before you start to launch your satellite. Somewhere in the middle could be what we call Airlander, which is a British company that's actually hybrid air vehicles. It's launched outside Bedford. And this is a 300-foot mega blimp. And we started to think about, could we mount a CMB experiment on one of the wings? So this is going to achieve a 10-kilometer flight altitude and have 3-week flight times. It hopefully doesn't crash to the ground, and therefore you are able to actually keep flying, and you can subscribe and pay for time on it. So as you get more money, you can keep flying. This is the idea. This is a very long time in the future, but it's cool to think about. And what could you achieve with this? So here is the tensor-to-scalar ratio error bar as a factor of 10 to the minus 3. If you are where the Atacama Cosmology Telescope is, it's up here. And this is all limited by the foreground subtraction, by the way. And if you could fly a CMB experiment on the Airlander, you would get down to here, which gets you most of the way to actually doing long-duration ballooning or an SPB. And then, of course, you have the jump to space, which you can never beat. But that's very expensive and a long time away. So I think it's worth thinking about. I've got 0 time, so I'm going to just present quickly what you can look forward to. And there are interesting constraints on fundamental physics, both before and after 2020, from the range of experiments that I've showed you. Tensor-to-scalar ratio, and also the spectral index of the tensor fluctuations, especially after 2020, is very interesting. And there are also interesting constraints on the neutrino sector. We might be able to even start to probe the normal versus inverted hierarchies, and could definitely get close to measuring the neutrino mass with very high accuracy. And also, this is underappreciated, but measuring the number of relativistic degrees of freedom in the early universe is actually a direct probe of thermal history 1 second after the Big Bang, and very, very interesting error bar on that as well. So I believe that the next generation CMB experiments have a big discovery potential for new physics if systematics are under control. And that leads to a transition between precision, getting smaller and smaller error bars, versus accuracy, actually getting to the right answer. I want to finish with Stephen's fingerprint on the CMB, and thanks very much.
Hold off our caffeine cravings for a few minutes. We have time for questions. I shouldn't have mentioned caffeine,
yes.
Should I?
Could you expand a little bit more on the discrepancy between the measurements of age and what the prospects for the future?
Mm-hmm. Yes. So if we go back to this slide, the prospects for the future, I think, can come from both sides. Okay, so especially in the distance ladder measurements, one of the main players is going to be Gaia. Gaia is going to be able to make a parallax-based measurement to the distance to the LMC, for example. And one of the uncertainties is how to jump from calibrating Cepheids in the Milky Way to calibrating Cepheids out in other galaxies, especially the LMC. And if you can get rid of that uncertainty, it removes a systematic uncertainty from that. Another improvement is going to come from being able to measure with BAO measurements, especially from DESI, at a whole bunch of different redshifts as well. So from cosmological measurements, you're going to improve that uncertainty. If I may phrase this in a different way, what we're not necessarily not seeing is something where okay, how to phrase this? If you have a cosmological model where the CMB measurement fixes the parameters of that model, but you're missing some new physics, then measuring it in the local universe might also mean that it's the difference between the concordance of the late time measurements will mean that you're going to actually get the wrong answer, even if your measurements are right. Right? So your local measurement might be right, your distance measurement might be right, but your cosmological model is wrong, and therefore your inference is wrong. In that sense, we have to also start to think about what are the new physics that could lead to that. And currently, there's a whole range of different models, but none of them actually quite fit. So it's worth thinking about what new physics could lead to these measurements if they're then taken at face value, that these measurements could both be real. But these systematic studies, especially in the distance ladder measurements, will need to be improved. And a lot of people are actually working on that. What usually happens is that each individual systematic is constrained separately, and then an assumption is made in this analysis stage and then passed on to the next one. So it's better to then have a full global model of your end-to-end data analysis and propagate the full set of uncertainties through. And people are now starting to do that for the distance ladder measurements using hierarchical Bayesian models. So I think this will also lead to an improvement in the inferences. Coffee time.
Any other questions?
Did you have a question?
Yes, we have one more.
Could you explain me a little bit more how? Could you explain a little bit more how the weak lensing is subtracted? Like, is it predicted? I didn't get it.
Yeah, it's a really good point. So basically, the main effect is that imagine that there was no weak lensing, there's no screen from the foreground structure. The spots would be in particular positions, but because of the screen, they're deflected, right? And you know exactly, given a certain amount of matter along the line of sight, how that deflection should work. It changes the statistics of the cosmic microwave background. It induces what's called a tri-spectrum into the statistics of the cosmic microwave background. By measuring that, you can actually invert it, and there's an optimal estimator to do that by Okamoto and Hu. And by actually using that estimator, when it's optimal, it's unbiased and minimum variance, then you can actually reconstruct a map of what you would see. This sounds very simplistic when I say it, but it's actually a really hard thing to do. But we have been able to do it.
Well, if there are, final question.
Was that method based on the assumption of perfect Gaussianity of the underlying spectrum?
Which method?
The one you just described?
I believe it does, but because we can independently actually measure the different bispectrum shapes as well, without that assumption, it's a very, very good assumption. Yeah. I don't think it necessarily affects the, okay, we can come to that, okay.
Well, let's thank Hiranya again.